let's do one more trig substitution that has some more interesting layers to it. Okay, so when we first look at this example, we might not immediately see it as a trig substitution because for a trig substitution, we need something like x squared minus a squared, or x squared plus a squared, or a squared minus x squared inside a square root. Like that's what we're looking for. So what we're going to do to get that is I have a square root that I want to get rid of. And I can't use a u substitution because there's no 2x or just even an x out front. To get rid of that square root, I want to use trig substitution, but I'm going to complete the square first so that I have a something squared minus a squared or vice versa. Could be a plus, we'll see. So the first thing we're going to do is we're going to complete the square. So I have x squared plus 2x, and if I take 2 and divide it by 2, I get 1. So x squared plus 2x plus 1, I square that 1 and I just still get 1, is a perfect square. But I don't want to change the problem, so I'm going to subtract 1, and of course I still have minus 3. And again, what I did was I found a perfect square, so I can rewrite this as x plus 1 squared minus 1 minus 3, which when I do minus 1 minus 3, I get x plus 1 squared minus 4. So let's replace my whole integral with this completed in the square version. So instead of x squared plus 2x minus 3, I have the square root of x plus 1 squared minus 4. And this looks more like an a squared, or an x squared minus a squared inside the square root. To get it to really look like a variable squared minus a squared, I'm going to do a u substitution. So I'm going to let u be x plus 1. And du is going to be dx. So that's a nice u substitution. So I get the integral of 1 over the square root. Now instead of x plus 1 squared, I get u squared, still minus 4, and dx can be replaced with du. And now it looks exactly like I would want for a u substitution, or for a trig substitution. I don't want to come back and deal with a limit, so I'm going to change my limits right now. So since u is x plus 1, when x is negative 5, u is going to be negative 5 plus 1. So that'll be negative 4. And when x is negative 4, u is going to be negative 4 plus 1, or negative 3. I'm just going to change those limits now so I don't have to back sub later. So now I have everything set up for a trig substitution, and that's what I'll do next. So I have a u squared minus 4. If I look at my table, then I'll see that I want u to be 2 secant theta. That's the trig substitution I want, because it's in the form u squared minus 2 squared. Also notice that I want du, well, I'll take du, and that'll be 2 secant theta tangent theta d theta. Because it's secant theta, so I might want an arc cosine later, I'm going to have this domain of 0 is less than or equal to theta is less than or equal to pi. And so something to notice is that u is negative 4 to negative 3. And that means that when I look at, so secant is 1 over cosine. When I look at cosine, let's see, u is 2 secant theta, or 2 over cosine theta, is negative. The places where cosine is negative on 0 to pi is from pi over 2 to pi. So I actually really only am going to allow my theta to be from pi over 2 to pi, where because my u is negative. And that'll come into play. Right now we don't need to worry about it, but that'll come into play when we finally take the square root. Okay. So for now we're going to forget our limits, and we'll bring them back at the end. But for now we're actually just going to do this trig substitution. So I have 1 over the square root, and I'm replacing u squared with 2 secant theta all squared, so 4 secant squared theta. I'm replacing du with 2 secant theta tangent theta d theta. Let's simplify this a little bit. So we get, I'll put that 2 secant theta tangent theta on top. I'll factor out a 4. 4 times secant squared theta minus 1. And now I'm going to use the trig identity that's connected with this, the fact that secant squared theta minus 1 is the same as tangent squared theta. I can replace this with tangent squared theta, which is what allows me to get rid of my square root. So that was the whole goal of this trig substitution, is to get rid of my square root here. So I have the integral of 2 secant theta tangent theta over the square root of 4 tangent squared theta. And now when I cancel my square root, I have to be careful because I might need a negative sign if what I started with was negative, because the square root always gives me back the positive version. So I'm going to go ahead and do the absolute value for now, and we're going to figure out what happens here. So tangent theta. Let's talk about tangent theta on this same interval. Tangent theta on pi over 2 to pi. So that's where I'm looking at. Well, tangent theta looks like has a bunch of vertical asymptotes. And if you remember, the vertical asymptotes are where cosine is 0, so those happen at pi over 2, 3 pi over 2. So from pi over 2 to pi, if I look here, indeed, tangent is negative. So to make sure that I get something positive in my integral, I'm going to introduce this negative sign to get rid of those absolute values. So that negative sign is to take care of the fact that tangent theta is negative, and the absolute value of that will be positive. So when I multiply by this negative sign, that denominator will become positive. And now I can actually cancel some things. So I get negative the integral of secant theta d theta. Okay, so I've written this in terms of trig functions, but I might feel a little stuck here if I don't know a sneaky algebra trick. There's a sneaky trick of how to integrate secant theta, and this will work similarly for cosecant theta. So the integral of secant theta, if I multiply top and bottom by secant theta plus tangent theta, something very nice will happen in terms of me being able to see derivatives. I can do the same thing with cosecant theta and multiply top and bottom with cosecant theta plus cotangent theta. So that's how you can integrate those functions. So let's do that with the secant theta so you can see what happens. Okay, so what happens? I wind up with secant squared theta plus secant theta tangent theta in the numerator, all divided by secant theta plus tangent theta. And hopefully you can kind of see where this is going. So if I decide to make W equal to secant theta plus tangent theta, then dW is the derivative of secant, or secant tan, plus the derivative of tangent, which is secant squared theta. And that is exactly what I have in my numerator right here. So I can sub in and get negative the integral of dW divided by W, or 1 over W dW. Of course, the integral of 1 over W dW is natural log. And normally I do a plus C, but I know I'm going to reintroduce limits in a little bit, so I'm going to wait. Now I plug back in my substitution. I'm going to back substitute for W. And I get negative natural log of secant theta plus tangent theta. Okay, so now I'm trying to back substitute my thetas for u's, my original u substitution. So I have u is 2 secant theta, which of course means that u over 2 is secant theta. So that'll tell me what to put in for secant theta. Now, of course, this means that 1 over cosine is u over 2. So I can draw a triangle to help me find out what tangent of theta is. So I have a right triangle with angle theta and 1 over cosine. So the reciprocal of cosine is u over 2. Cosine is adjacent over hypotenuse, so 1 over cosine will be hypotenuse over adjacent. So the hypotenuse could be u, the adjacent could be 2. Of course, that means that 2 squared plus my other leg squared is equal to u squared. So this other leg is u squared minus 4. And that means that tangent of theta, which is opposite over adjacent, becomes the square root of u squared minus 4 divided by 2. And that's what I'll put in for tangent of theta. And now I'm finally ready to evaluate this antiderivative at my limits for u. So when we changed our limits for u, they went from -4 to -3. So I'm going to use the fundamental theorem of calculus, and let's see. So my upper bound is -3, so it'll be -3 halves plus the square root of 9 minus 4 over 2. I'll subtract the negative natural log, and now I'll plug in -4, so -4 over 2 plus the square root of 16 minus 4 over 2. I get negative natural log -3 halves plus square root of 5 halves plus the positive natural log of -2 plus the square root of 12 halves. And of course I could find a decimal approximation for this, but we finally found this integral. In summary, we had several steps here. This was a very interesting example. We completed the square so that we could see we needed a trig substitution. That was the first thing we did. And then we did a u substitution for the x plus 1 so that we could see that this truly was a trig subintegral. We knew that it was a u squared minus a squared form, so that told us to use a 2 secant theta for our trig sub. And we noticed our limits gave us a domain for which we were considering this trig substitution. And that was essentially when cosine was negative, and it turns out that tangent will be negative as well on that subinterval. So we did our trig sub. That allowed us to cancel the square root, but because tangent theta was negative, we got this little negative sign right here. So for the limits that we were using, tangent theta wound up being negative on the interval that counted. And that negative sign will carry through. Then we wound up evaluating secant theta, and we used a sneaky trick to do that. Another u sub, which became a w substitution because we already used u, and we were able to finally back substitute our way to evaluating this integral. And that's another example of trig substitution.